So, last one of today, we're turning off the lights, so it's getting dark. Hello everybody, I'm Victor Remmers. I'm from the original Vrijhof Anchors. I joined Vrijhof close to 17 years ago. So in the meantime, I do some designing like the Stev shark racks. I do all the FEA for Vrijhof and all the offshore testing as well. And now and then they send me out for tensioning. So today it's not about mooring anchors, but about our tensioner, which is actually older than what I am with Vrijhof. But it's a technique to use a limited vertical force to get enormous forces in a horizontal line. And that works very well. This is our track record. You won't be able to read it, but I won't be staying long for here because, it's interesting. So, we have a horizontal line. The Stev tensioner will lock itself on the chain. We can only work on chain, and there cannot be any flexible component in the line, so that needs to be chain as well. And when you then go up, this horizontal line will feel an enormous force towards each other. In that effect, that 100 tons vertical will create, roughly, rule of thumb, about 200 tons in the horizontal line. We can go actually slightly higher than that. But I have a small video which you can find on YouTube as well, and which explains the operation of a tensioner quite well.
The Stev tensioner is a tool designed to make the installation of mooring spreads more efficient. It can be used to proof-load drag embedment anchors, driven piles, suction anchors, and even quayside bollards. Its design is based on the principle that when a vertical load is applied to a taut horizontal cable, it will generate greater horizontal reaction forces at the foundations. Compared to the conventional bollard pull method, the Stev tensioner can generate higher horizontal loads. The required vertical pulling force only needs to be 40% of the horizontal pre-tension load. This enables mooring spreads to be installed from smaller and less advanced vessels. Vertical loads generated by a crane or winch are also easier to control than loads from bollard pull. When lifted, the Stev tensioner locks onto the active chain and lifts the mooring spread off the seabed, which pulls the anchor legs inwards. When lowered, the slack chain is passed through the Stev tensioner, maintaining a taut horizontal line for the next heave. This repetitive cycle applies tension across the mooring spread, providing an accurate, controllable proof load. The integral load pin measurement is transmitted to the surface and recorded on the vessel. The Stev tensioner can be used to make installations more efficient in 3 ways. Firstly, in symmetrical mooring patterns, 2 opposite anchor legs can be tensioned at the same time. Secondly, for systems that use a single anchor or non-symmetrical mooring patterns, a reaction anchor can be used to create tension in the opposite mooring line. Thirdly, when the spread is made up of equally spaced mooring lines, a 3-way tensioning system can be used, reducing the overall installation time. The Stev tensioner can apply loads of up to 1,250 tons and can be used with chain or wire mooring lines of any size. There are several advantages that the Stev tensioner has over alternative anchoring tools. Compared to conventional installation methods, the Stev tensioner can reduce the number of proof load operations by up to 50%. The required applied load and hence winch capacity is reduced significantly, meaning that smaller, more cost-effective vessels can be used. Also, less vessels are needed to get the job done. In total, the Stev tensioner can reduce the cost of installing anchors on the seabed by as much as 40%. The tool is portable and lightweight, so can also be airlifted. If you're used to traditional equipment rental services, the benefits of working with Vrijhof will be immediately clear. We provide engineering, hardware, and supervision as a standard package. The Stev tensioner by Vrijhof, enabling installations.
Still our old logo. Looks still far better than the Delmar one, but don't tell Sherman. On the right-hand side, you can see one of our cable winches, which is having an umbilical cable which goes down to the load cell of the Stev tensioner in case we are in shallow water. Later on, I'll also show you the acoustics so that we don't need any cable. On the left, you see actually a truck arriving, in this case, at the Mediterranean with our VA1000 and the little container which contains the winch, which will be in total hoisted on the vessel, because we were called for a bit of an emergency as the competitor's copy tensioner didn't work. So that was last year. The vessel you see is the Horizon Arctic, so a nice big one. How is it actually hooked up? So basically our container is put on the side. You can see the Stev tensioner over there on the side. Just make sure that you only do this with the sea state, which will remain the tensioner in a non-sliding position, because you don't want this 7 tons of solid steel chasing you around the deck. Yeah, also it needs to be secured as the anchors as well. So basically it's on the side. First you get your both chains from the anchors. You get them into the shark jaws. You drag the tensioner just with your tugger wires. You can easily slide it along the deck and you put it where one chain will be going through the tensioner and the other chain will be connected directly to the big shackle with the load pin. So very simple deck operations. Then when everything is connected, the retrieval wire is connected to the shackle which is used to hoist the tensioner back on deck again once the operation is done. And then everything is brought under tension and the whole stuff is released from the shark jaws and put overboard. Most of the time before this you actually haul in some of the active chain going through the tensioner, so it's just pull it dry through the tensioner to get a little bit of spread between your lines below the vessel. Otherwise the whole stuff can start twisting up at below the vessel, and that's what you see happening over here. A little bit of separation between the vessels, so this is from the ROV looking up. There you see the tensioner sliding down along the line, and we try to remain also over here. So basically what you need to do with your vessel is you have to heave the active chain going through the tensioner. You have to lower with the retrieval line, you lower the tensioner, and in the same way, because you're moving with the tensioner in the direction of the active chain, you have to move sideways. So the vessel has to perform 3 tasks in the same time, which, if you're new to the operation, which will take them 1 or 2 operations to get used to. After that, the operations start to speed up, everything starts to get as usual. Also, when the tensioner is unlocking, so when you, after a heave you go down, you can see it's a pretty violent act. This is 7 tons of steel dropping down. And that will be caught by the same chain a number of links lower. You can hear this on the vessel. When you're standing on the bridge, you hear a definite rumble going through the whole steel operation. And once you're down again, you can go up again. And the idea is that after some of these heaves, your tension is going up. And in this case, you get your required target force. And here is typically your last heave. We're going up. Basically, what we need to do is go higher than the target force, because at the end of that heave, we will stop the winch, put it on the brake, and just see what happens. And what you see here, over here, the decay line is basically the anchor still creeping through the soil to a point where it's in balance with its force. And the requirement from class will be that after a holding period, and that's depending on class, strangely enough, so you have class like B and DNV and BV, they have 15 minutes holding period. If you go to ABS in America, you have 30 minutes holding period. But during that complete holding period, your tension on your line should not drop below the target force. If that's the case, then your surveyor will stamp you make a screen dump of, because this what you see over here is a real screen dump of actual tensioning operation. So this one was really much okay. And then they will just stamp your screen dump and say, okay, this is the proof that this line has been tensioned correctly. So you see over here, the first heave taking up a lot of slack, and actually it's not adding that much tension, then the slack is gone, and the first heave actually went to something like, where are we? Some 300 tons. Then we go down again with the tensioner, so this is basically lowering the tensioner, and over here it starts sliding along the chain, that's this rumble here, and then you start again in the same way. So the only operation you do at the vessel at that point is your active chain, you go up and down. You leave everything else, your umbilical cable, leave that in place, you just are moving the tensioner. In this case, with the second heave, we just managed to get to the test tension requirement. And that was not high enough to make a chance to get to the holding period. So we went again, and the third time we took some pretty close to 15% overshoot. And as you can see, this was pretty solid soil, so not a lot of decay, 15 minutes, absolutely no problem. So this is textbook tensioning, everything okay, everybody happy. Nice day. So we went to the next location. This is actually all in the same field. This one has a lower required load. The other one needed to go up to, had a target of 599 tons. This one had a lower target, 422 tons. And again, you see every heave you go higher. The third one, we thought we had it, but nah, just before we reached the end of the holding period, we dropped through it. So, but we had still heave height to spare. So we took up the tensioner a little bit, and then basically what happens is that it almost continues where it left off. So in that point, we still managed to get our 15 minutes. And again, surveyor, client happy, everybody happy. Next one. Ooh. That one was a more serious one, because the second heave was already crossing the target, but stopping it, we could see the tensioning dropping like a stone in the water. Yeah, completely down, no chance of getting a holding period, so we went again. And we stopped again, and again it went down like crazy. Yeah, you see the tensioning dropping up enormously. This is an indication that your anchor is moving quite far. So we said, okay, let's do it the fourth time. We're still not outside our box, so we have room to spare. In the fourth time, I remember, is that actually what happened is that before we reached the peak, while we were still heaving upward, the tension line was already starting to dive down. So then your client is starting to get nervous, because they're really like, oh shit, this is not going right. No, this is not going right. So we said, okay, still room, we take another one. You can see near the 5 that the anchor seems to be getting hold of something. So we said, okay, let's try again. But still, it dropped too fast. And we almost already suggested, okay, let's just get this anchor out, put it in a different fluke angle so that it gets more holding capacity. And just, no, we still have room. Can we do one more? Okay, we do one more, and probably the result will be the same. So in this case, yeah, actually it wasn't too bad. And the decay curve was showing something that like 15 minutes we were just above target. I actually advised them, look, I wouldn't trust this anchor. I would just do another heave, because this is not what you want to see. Then you have to deal with the client and the surveyor, because it's not my call. I'm just generating data in that point. So the client was, yeah, but we're 15 minutes, we're above target line, so this one should be approved. And in this case, the surveyor actually approved it, because it was according to the rules. Yeah, well, if it would be my rules, I would say that, nah, that doesn't seem right to me. Later on, we actually produced the last heave and did a bit of extrapolation on that, least square minute. And yes, it came to a 429-ton asymmetric value, where the required value was 428 tons. So 1 ton, really? This was actually scary for me. So after that, I contacted DNV, Jan Holme in Norway, and he was really like, oh, this is interesting for the rules and stuff. So this guy was having a party over there. By the way, this is the Rigfleet seminar actually from last year. This one was Jan's presentation. So in case you just think that these Norwegians are all very icy, cold people, think again. Okay, another thing we noticed during this tensioning is that when we were under a high load, then of course your vessel DP system gets a bit messed up. Because you're having this point at the stern roller where you have this big force pulling down. If we had these anchors going to 600 ton, tensioner going to 700 ton in the horizontal line before we get to the decay, 700 tons means you have close to 350 tons in your chain over your stern roller. Well, this was working chain, otherwise I'm pretty sure that Dag Burre would have something to say about it. But okay, so you have big vessel, 350 tons down on your stern roller. Your DP system is going to react on that. And what Kongsberg told me, that because these guys were actually having some troubles with that, and you can actually see that this little weave you see in the data was the vessel going at least 10 degrees starboard to port, starboard to port. It was searching for heading. So somehow it was overreacting to the point. So Kongsberg told me, look, they have, in this case, a luxury vessel, they have a tension interface on the DP system, so they could move the pivoting point backwards, and then they advised to adjust the value of the gain as low as possible, that it doesn't react that strong. So any captains who will ever use a tensioner, you can do something about the vessel overreacting on this additional external force, because you're really doing something. This is actually already quite a while ago, some 10 years. We did some tests with an acoustic tensioner, because if you're going to deeper water and you have this umbilical cable, that will be affected by water, by currents and stuff. So up to 100 meters of cable next to the chain going down, that's still quite okay. You now and then damage a cable. Normally we come with 3-4 spare cables, so that shouldn't be an issue. In this case we tested acoustics, and we went to 1,440 meters, which is about the limit of a portable suitcase, because this vessel didn't have any high-pep system. It was too old. It was the Maersk Seeker, 210 tons bollard pull, and we were doing 2 Stev shark anchors of 22 tons at a vessel of 1,440 meters, completely blind. There was no ROV. So, interesting. What we do on the tensioner is we put a Kongsberg C-Note on there and have it communicate with a serial end cap with our load cell. Then our pin is also a digital one, so it produces digital values for the tension it sees. And apart from that, we can put on even a subsea display that in case you cannot acoustically reach it anymore, you can just go down with your ROV, put the light on the display, and it will show you the force in tons. So now we can actually communicate with the high-pep system, and we made an addition to the Kongsberg APOS system that you can actually see in the Drent graphs. You can see your tensioner value, and you can also see the orientation. And this is the actual screen on the CPAP 30 suitcase we had with us. And you can see the sensor strain that's going up to roughly some 260, 270 tons where we were, the yellow line. And the depth line, you can see that actually over here, of course it's inverted. This is 1,400 meters, and then we go up to 1,330 meters. And a little bit of signal quality, but well, we got at least some data from the deep, because we were not seeing anything what we were doing over there. It was purely on instrumentation that we were having this data. So this is how the data looked. half an hour holding period, 267 tons, which is, for this water depth and a vessel only capable of bollard pull 210 tons, is actually not that bad, because you have quite some cable and wire rope hanging down to the seabed. It took us half an hour to get the anchor to the seabed over there. So that's the acoustic one. We can do that on various tensioners. Now we have backpack packages to put on the tensioners, so we can almost supply the complete family, and we have a complete family of them. The one I used in South Africa was the 84 mil. That's specialized for 84 mil chain. We have a couple of smaller ones, the VA 600s, of which we rebuilt the older one in especially for 64 mil chain, because that one was of mild steel, and we saw that mild steel is not enough, so all the newer ones are based basically Weldox, Hardox, that kind of material. So then we have the VA 1000, which we used in the Mediterranean. That one can go to 1,000 ton of load. And every tensioner has its own range of chains which we can accommodate, which we can have filler plates for. It can be with canters, without canters. We will make sure it fits and send it accordingly. And lastly, we have the big one. That's up to 170 millimeter chain if there are no canters in the line. But it also weighs. It weighs 17 tons in air. So around 15 tons in water. But for this one, we have a whole set of filler plates which you can bolt in to suit smaller chains. So that's the tensioner department. And then we have lately, and there's quite some interest in those, these, you already saw them in the video of Ocean Installer, these Stev adjusters. In this case, what you see over here are Stev adjusters of 120 millimeter chain. So one of these is 16 ton. This is a small simulation I did. In this case, it's the idea that we have a section of mooring chain, and we take the tension out of that section. So we make a parallel chain with the Stev adjuster, and then we tension up. I put a little bit too much force on here because it's actually pulling the chain over there, but the general idea is still the same. You can see every second link, the cradle will drop down in the chain, and as soon as you then reverse the movement, it will completely lock up the chain. So first you start with low tension, then you see everything coming under tension, and at a certain point the tension in the existing mooring line is completely gone, and you can basically take it out, replace it, do whatever you need to do over there. This is also the way DNV actually prefers it, having the Stev adjuster on the seabed, because that's the most safe location for this kind of mechanisms, as it is not moving the chain. Yeah? Once you stop, the chain is also stationary in there. As soon as it's in the line, you have this big mass showing all kind of movements on the chain sections. The only concern for what you just saw is that in this case they hooked up the operation with big shackles going through the existing mooring chain, which is the one now in the bend, and that will cause some additional stresses in your original mooring line link. That is something that up to a certain tension that's acceptable, but pretty quickly you will go above the level that DNV will like this kind of method to be applied on an existing mooring line, because that link will be in your mooring line again when the shackle is removed. So as soon as you make too much life damage in that link, then they will say that this is not the best way. We're actually thinking of getting something to get that out of the way and do it in a bit more nice way, but that will take us a little bit of time. So, it's getting dark. Questions?
Thank you, Victor. That was good. Any questions from the room? No, that was great. One question for me, I didn't quite pick up on it, but the 3-leg system you can tension with one. What does that look like in terms of the connection to the tensioner?
As usual, only on one side you have a tri-plate and you split the
so
lines.
you're using a tri-plate.
Yeah, so and you will have equal tension in all the 3 lines.
Yeah. Have you?
It will self-center it.
Yeah. Have you done that operation?
No.
Okay.
But
Yeah,
we know it should work.
Yeah. I guess that would be pretty interesting for the wind market.
If you're having the right spread length, yes, that's all depending on the length of your mooring line.
Yeah.
That needs to be within a certain range, and otherwise you need to go to reaction anchors.
Okay. And the video you showed the model when you're pulling it through, what is the consideration for overpull? I know we have the stopper plates we can put in, but how easy is it to release?
Okay, no, the overpull is quite easy. There is, on the cradle we have this little eye, and basically what you do is you put a line to that eye, you make sure there is some tension on it. You don't need actually that much, maybe 1-2 tons at the most. And then you retension the chain, and as soon as you pull the chain out of the pockets in that cradle, which you see moving, then the cradle will help up, and if you keep it up with your line, you can just release the chain again, and you can reverse the whole process as far as you want.
Okay, excellent. And is that ROV operable?
Yes, you could do. Possibly, I'm not sure if an ROV is capable for the bigger versions. But what you could do is put a kind of subsea floater which you inflate at that location, and then it will take it up.
Excellent. Okay, thank you. Any more questions? Oh, easy now, easy. Someone wants to get home.
He's thirsty.
Yeah. Okay, excellent. Thank you very much, Victor.
Okay, you're welcome.